So we're getting into showing that something is continuous at a particular value or discontinuous at some value. There's different types of discontinuity. So far in our mathematical careers, if you haven't had calculus, you have looked at something being continuous if you could draw it without lifting up your pencil or your pen. If you had to do that, then that kind of showed us that it was discontinuous at that value. We're going to now show this more mathematically, that something is either continuous or not continuous at a particular value. So if you look here, I have 4 different graphs in front of us. And that first graph that we're looking at, notice that we have an open circle when x is equal to 2. And so I can see here that this is discontinuous at x equals 2. The thing is, if I go in and I say, okay, let us choose. So when x equals 2, we can choose its y value to be 1. We're going to let y equal 1. Or another way to write that is f of 2 is equal to 1, right? If I did that, if I define that with this function y equals f of x, then notice that that point, that's no longer an open circle there anymore. And it's solid. And so this type of discontinuity is called a removable discontinuity. So if we go to the next graph, though, notice what x equals 1. We have a jump in there. There's no way that we can define some value in x equals 1 to make this so that it's continuous. And so in this case, we have a jump discontinuity. That third case, and we'll get into that more this week when we're graphing rational functions and we have different types of asymptotes. Notice in this case, when we have x equals 0, we have a asymptote, a vertical asymptote here. And so this is vertical asymptote. That's why we have a discontinuity, and in this case at x equals 0. And the last type that we have is if we graph y equals sine of 1 over x. In this case, it oscillates back and forth really, really fast as we get closer and closer to x equals 0 on the left and the right. And so in this case, our discontinuity is because of the oscillation. Okay, so those are the 4 different types of discontinuity that you can come up with, and that's what they look like. So let's just go through what it means to be continuous and the definition. Well, in order for something to be continuous, first of all, it has to be, we have to think about our domain of our function. So just be aware of that while we're talking about this. So the following says, let C be a real number that is either an interior point or an endpoint on an interval in the domain of F. Okay, so if we're talking about our domain, we say that our function F is continuous at C if we look at the limit as x approaches C of f of x. This is equal to as if we plugged in C wherever we saw an x in our function f of x. So you can see that I have a picture in front of us on the right of that diagram. And so notice here, as the limit as x is approaching C, And in order for a limit to exist, if it wasn't an endpoint on our domain, remember the limit as x approaches c of f of x on the left, this left-hand side, that's a solid circle there. So this is equal to f of c. And that's the same thing as the limit as x is approaching c on the right-hand side. Coming in on the right-hand side, that's solid. It didn't matter if it wasn't solid though, right? Because that's still the limit would have existed from the right of f of x. So the limit on the left equals the limit on the right, and it's the same value as plugging in our c value into our function f of x. Okay, but if it's an endpoint, then we got to be careful. The limit as a function f is a right continuous at c, or continuous from the right, if the limit as x is approaching c of f of x is equal to f of c. So in here, if I'm coming in on the right-hand side, this is a solid circle, and we're getting back the y value as if we had plugged it into our function. Same idea from the right. So we say the function f is left-hand continuous at c, or continuous from the left, if we're coming in from the left from our f of x, and we get that y value. So really, technically, we need to show 3 things to show something is continuous at some x value. First of all, we need to show that that value exists at x equals c. It's part of our domain. C lies in the domain of f. We have to show that the limit exists. So limit as x approaches c of f of x exists as x approaches c. So we have to show the left-hand side and the right-hand side are equivalent. And we have to show that that limit that we found as a limit as x approaches c has to be the same thing as if we had plugged c into the function, that same y value. So those are 3 things we are showing when we're looking for continuity, or to show that it's continuous at a particular value. So there was a great question when the video was paused about this removable discontinuity. So if it's a removable discontinuity, there means there's some open circle there that if we go back and define the x value to equal some y value to make it so that we can make this continuous at that value, then it's called removable discontinuity. And there are other 3 examples of looking at these graphs. There's no one point that we can define, no one x value. I can say x equals this one y value to make this continuous, right? Because there's an infinite number of x values I could put in here, or letting x equal 1 to be different y values to make this continuous, and it doesn't work. So same thing with the other examples. So it's only removable if we can define x at a particular value, y value, to take away that open circle. Okay, so let's look at this following example. And you're given a picture of a graph. And if basically this is a piecewise function, I can see this is defined, well, in multiple different places, right? I have this piece in here, so this is one function. I have this piece in here, so this is the second function. I have another value in here. That's one function. A point, that's a function, and this is a function. Okay, so if I was given this and I had to graph it, I would have 5 different equations for different x values. Thanks. So looking at the graph below, answer the following question. So at which points does a function fail to be continuous? Okay, so first of all, I can see what my domain is, and you should be able to tell what your domain is. You should be able to find the domain given an equation, and you should be able to find the domain looking at a graph. And notice our domain, remember, are all our x values that we're using in this case on our graph. And so notice the smallest x value we have is -1, and there's a solid circle there. So we're going to include -1 as part of that. And then notice that at x equals 1, there's a jump there, but it's actually defined at 1. So there are a couple ways we can do this. We can split this up into different interval notation and use unions, but basically every value that I see, like an open circle, I see that it's defined, like in this case, x equals 2 is defined there on that function. So I see that this is looking at all of my x values between -1 and 3. But where am I having problems? Well, notice that at x equals 1, there's a jump in my graph. And I can show this, that it's discontinuous, by showing that one of those, at least one of those, numbers, either f of c exists. So in order for it to be continuous, f of c exists. So if I show that f of 1, it actually exists because of this solid circle, right? So f of 1 exists. And I know that it's equal to my y value of 1. I need to show that the limit exists. But right there, I can see my limit doesn't exist, right? In order for a limit to exist, the left and the right-hand side have to equal. So if I was looking at the limit as I'm coming in on the left-hand side, so following my graph as I'm coming in on the left-hand side, the y value that I'm approaching, I don't actually hit it, but the y value I'm approaching is 2. And if I looked at the limit as I'm approaching x equals 1, as x is approaching 1 on the right-hand side of f of x, as I'm following this in on the right-hand side, I'm getting a y value of 1. And so right there, those are not the same. And so the limit as x approaches 1 of f of x does not exist. And so right there, that shows me that step 2 that I had to show, in this case, so it's defined as step 2, that the limit doesn't exist, so it can't be continuous. So therefore, if you've had my husband before, you might know he uses those 3 dots that kind of form the triangle. That means therefore in mathematics. So therefore, it's not continuous. At x equals 1. Sorry, yeah, 1. So I can see also, right, and we talked about it, you can determine that that's a jump discontinuity. And so there's no value I can plug in there that would work. And so this one is a jump at x equals 1 is a jump discontinuity. And so I also notice that there's only one other value where we have a problem, and that is when x is equal to 2. There's this open circle here. So it's discontinuous at x equals 2. F of 2 exists, right? There's a point when x is 2, we have a point, y is 2. Our limit x actually exists, right? Because our limit as we come in on the left is the same as we come in on the right. So the limit as we're coming in on the left equals the limit as we are coming in on the right. And so since we're getting that same y value, the limit exists. And that y value we're getting back is 1. But since the limit as x approaches 2 of f of x, notice that this does not equal f of 2. Therefore, it's not continuous. That third condition of the continuity test that we had down there didn't hold true. But notice that this one's removable. At x equals 2. So if we define, so when x equals 2, let y equal 1. So x equals 2, and we let y equals 1. Notice that this now is solid here. And so it's removable. Okay, so we have in front of us a theorem, properties of continuous functions. So just kind of think back when we were looking at limits and we were looking at limits of an equation, we were able to use these conditions of limits and break it down so we can make the limits simpler. Kind of the same sort of idea with these continuous functions. If we know our functions are continuous, so if our function f and g are continuous at some value x equals c, then we can say that the following algebraic combinations are also going to be continuous at x equals c. So it's continuous of a function f at x equals c. We can add difference. It's still going to be continuous. If it's continuous in a function, I multiply it by some constant, then that's still going to be continuous. If I take the product of two continuous functions at a value, it's still continuous. The quotient, only thing we have to provide there is we can't divide by 0. So we just have to say if it was continuous at x equals c for our denominator, it just couldn't be equal to the 0. We know that if a function is continuous, then raising it to a power, it's continuous. We have to put on that little stipulation that it's a positive integer, right? Because if I raise a function to a negative integer, -1, and that's not representing the inverse, And this is the same thing as 1 over f. Remember, make our exponent positive. And so then I have to start getting worried if my exponent was negative. And so that's why that piece is in there. And roots. So if our function f is continuous, then we can say the nth root of f is continuous. We got to be a little bit careful though, because if we're talking about roots and we're looking at domain, if we had an even powered, like a square root, we can't have negatives under the radical, or a fourth root. So it's okay if our index was odd, because we can have negatives under the radical, but it's continuous provided that it is defined on the interval containing c, where n is a positive integer. Okay, so we're going to use those facts. We're not going to prove any of them, but we're going to use those facts to look at limits. Actually, to see if a function is continuous or not. Okay, so our first example. At what points are the function continuous? We have y is equal to 1 over x plus 2, and that x plus 2 is quantity squared in the denominator. And then we have outside of that fraction plus 4. So when we're looking at where this is continuous, we actually really want to look at where we can have problems, or where is this undefined in our domain. And so if we have a rational function, if we have some variables in the denominator, we can't have our denominator equal to 0. And so we're really worried about, the only piece that we're really worried about is x plus 2 quantity squared cannot equal 0. So we could solve for when that's equal to 0. I noticed that this is a perfect square. I can use my square root method where I could take the square root of both sides. Right? That square root of 0, 0, taking the square root of a square, that would just give me x plus 2 cannot be 0. Subtract 2, so x cannot be negative 2. So this is going to be continuous everywhere, because I know that at x equals 1, I can break this down, right, as different functions. It told me that if it's continuous for quotient, which this is a quotient, so it's continuous at 1, and that's a constant. It's continuous at x plus 2 quantity squared. The only problem is we can't have any value which sets it equal to 0. So x can't be negative 2. And then it told me it's continuous if I have some function continuous plus some function continuous. And I know the function 4 is always continuous. It's a horizontal line. Then the whole thing is going to be continuous. So the only thing that we can't be is negative 2. So when it's asking me at what points are the values or the function continuous, we're looking at everything from negative infinity up to negative 2, not including, so that's where we put the parentheses instead of a bracket. Union, we're looking at all the x values from negative 2, but not including, so having a parentheses to infinity. So again, we want to look at this example. We have y equals x plus 2, and then that's all over cosine of x. And we want to find where is this continuous. Well, I know my numerator again, x plus 2, it's a line. If I just graph that, that's continuous everywhere. If I just looked at my denominator, cosine of x, it's a trigonometric function, and that is also continuous everywhere, cosine of x. problem is I can't have cosine of x, what's in my denominator, equal to 0. So let's go back and let's think about when is cosine of x equal to 0. I'm going to actually put equals instead of not equals right now. If we're thinking about the unit circle, remember cosine was the x value of your point. And so when our x value is 0, that was when we had pi halves. Over here, we had 3 pi halves. But it's periodic, right? And so every 2 pi, that's going to be the case. Or another way to write that, every pi, right? So as long as I say, okay, x equals pi halves plus, if I just add pi to that, I'm going to say times k. And I need to be careful because I can't have that as a half or a part. K is equal to an integer. Okay. So just kind of notation wise, mathematically, that kind of funky, kind of looks like a capital E is mean contained in. So, and that funky Z looking capital Z, that means integers. So K is an integer.
I think we're all having a
Yeah,
similar
I can't
issue. We can't
Yeah.
see.
Yeah.
Don't
Okay.
exactly know what happened.
Okay, thanks for letting me know. Oops. And like just everything disappeared. Okay, so it looks like things are freezing. And I can't pause the video. See if I do this. Okay, so this happens sometimes and it hasn't happened in a long time. I'm just gonna go through and I'm gonna do the task manager. Let's see. I'm hoping that took care of things, and it doesn't. Okay, so there was a little bit of tough technical difficulties, and I'm just going to restart this problem. We're looking at where it is continuous, and we talked about that the numerator is continuous, x plus 2. We know cosine of x is continuous everywhere. The problem is that this is a rational function, and we can't have values which set our denominator equal to 0. So we were just kind of recalling, going back to trig really quick, and looking at the unit circle when our values of cosine was 0. So recall cosine was our x value of a point, and this would be, right, when x is 0, when x is equal to pi halves. When we get down to 3 pi halves, but it's also cosine of x is also periodic. And so that happens every 2 pi, but we can actually even say, no, well, that happens every pi. Because from pi halves to 3 pi halves, that's a pi. If I add a pi to that, that's going to give it, back to where values of x, which set cosine equal to 0. And so how we can write that, if x is contained, sorry, what did I say? X is equal to pi halves plus, if I add some pi to that, well, if I add, or a multiple of pi, so pi this way would go there, but remember I could add or subtract pi, that would get me over here. So adding some multiple or subtracting some multiple of pi to pi halves would get us to those areas or values of x which set cosine of x equal to 0. And so this is where I said, let's say pi times k. And we're going to just define that k is contained in the sets, and that's where that funky came in, contained in the set of integers. and you can denote integers, and I don't have to do the positive integers. We can denote integers by that funky z. Okay, so these are the values that set cosine of x equal to 0. But we actually don't want cosine of x to equal 0 because that's where it's undefined. That's what sets our denominator equal to 0. And if it's undefined there, then it also means that it's discontinuous there. And so this is going to be continuous such that we can put this in set builder notation such that x, or the set of x that such that x does not equal pi halves plus pi k, where k is equal to an integer. The next example says y is equal to the fourth root of 3x minus 1. I need to look at my domain because it's not going to be continuous anywhere where it's x is not in the domain for that function. I notice that I have a radical and my index is 4. So I have an even powered radical. And so I can't have values of x which set my denominator equal to a negative number. I have to have all my values of x, 3x minus 1, has to be either greater than or equal to 0. Okay, so I want to solve my inequality. I notice it's linear inequality, so I don't have to worry about finding critical numbers or anything. I can just solve. I just have to worry about dividing or multiplying by a negative, and that would flip my inequality sign. So I could add 1 on both sides. I know 3x has to be greater than or equal to 1. And I could divide through by 3, so x has to be greater than or equal to 1/3. So it's going to be positive for all values of x where what's underneath our radical is positive. And so it's also going to be continuous there. So it's going to be continuous when x is greater than or equal to 1/3. So this next example is a little harder than the other ones. We were just worried pretty much about what was our domain. Because of those rules of continuity, we could show that it was continuous everywhere in the domain where it was defined. So in the next example, we have a piecewise function. Our first equation of f of x is x cubed minus 8, and that's all over x squared minus 4. And this is defined for all values of x such that x doesn't equal to 2 and x doesn't equal negative 2. If x is equal to 2, we're going to have a function that is equal to 3. And if x is equal to negative 2, the function is equal to 4. F of negative 2 is 4. So in order for it to be continuous, the left and right-hand side limits have to be the same. The limit has to exist. And that value has to be the same. So in order for it to be continuous at x equals 2, we want to show that the limit as x approaches 2 of f of x, we're curious, is this equal to f of 2? Okay, well, let's look at the limit as x is approaching 2 of x cubed minus 8 all over x squared minus 4. Remember, we always did direct substitution. That's where we started. And so if we plugged in our 2 in here, we get 2 cubed minus 8 all over 2 squared minus 4. Unfortunately, 2 cubed is 8, 8 minus 8 is 0. 2 squared is 4, 4 minus 4 is 0. So unfortunately, we had gotten that indeterminate form. And so that's where that limit didn't tell us anything, and we had to start manipulating it. So factor was one way to start manipulating. I noticed that I have an x cubed minus 8. So just kind of review about factoring. If you notice there was a difference of cubes there. So a cubed minus b cubed. If you have a difference of cubes, that's factorable. And that factors as a minus b all times the quantity a squared plus ab plus b squared. So I can factor this. And the value that I'm cubing is x, so it's x minus what I'm cubing for the second term is 2. So x minus 2 all times my a value, in this case is x. I'm sorry. Yeah. And my b value in this case is 2. So a squared is x squared, opposite sign plus ab, so 2x plus b squared, which is 2 squared is 4. All over x squared minus 4, that factors as x minus 2, x plus 2. Notice our factors cancel of x minus 2. And so now when I look at the limit here, I can just do my direct substitution again, and hopefully I don't get that indeterminate form anymore. So plugging in 2 wherever I see an x after simplifying. So I get 2 squared, that gives me 4, plus 2 times 2 is 4, plus 4, all over 2 plus 2, which is 4. So that gives me 12 fourths, or 3. So we just found that that limit as x approaches 2 is equal to 3. Well, let's see what f of 2 really is, though. When x equals 2, my y value is 3. So f of 2 is also equal to 3. These are the same. That's what had to hold in order for it to be continuous at x equals 2. So we're continuous at x equals 2. So the only other limit that we're worried about is when x is -2. So let's look at the limit when x is -2. Same thing's going to happen. If you go in and do direct substitution, you plug in -2, you're going to get 0 over 0. So that's where we had to factor. We already did all that work before. So we saw that the numerator factored as x plus 2 all times x squared plus 2x plus, I'm sorry, it was x minus 2. All times x squared plus 2x plus 4. And the denominator was a difference of squares that factored as x minus 2x plus 2. Cancel like factors. And so when we do direct substitution, plug in -2 now wherever you see an x. So if we plug in -2 wherever we see an x, Notice we get 4 minus 4 plus 4 all over 0. This is 4 over 0. This is undefined. So the limit doesn't exist. So if the limit doesn't exist, then it can't be continuous at x equals -2. And so the only problem spot we were going to have was where our equations changed. And that was going to be at x equals 2 and x equals -2. And so this is going to be continuous everywhere except for that x equals -2. So it's continuous from -infinity to -2, parentheses, because we're not including -2, union -2 to infinity. A piecewise function, you got to be careful and look at the limits for each equation and see that that was that exact value is what it's defined for. Okay, so I did make an error and there was a great question. If we went in and we plugged in -2 wherever we saw an x in this function right here, x cubed minus 8 all over x squared minus 4. Well, -2 cubed is -8, minus 8 is -16 over 0. And so I was just saying, well, that if I had plugged in, I was just assuming that it was 0 over 0, but it wasn't. It was -16 over 0. We didn't have to go through this method of factoring because that's not an indeterminate form. It is undefined though. And so we can just say that's undefined. And so one of those did not hold conditions. That condition didn't hold for it to be continuous. So we can say that the limit doesn't exist.